Imagine standing on a world where it rains glass. Not metaphorically, not poetically, but literally. Shards of silicate hurtling sideways through the atmosphere at over 2,000 kilometers per hour, driven by winds so savage they would reduce any concept of civilization to dust in seconds. Imagine looking up from that hellish surface and seeing not a gentle yellow star but a blazing blue furnace so intense that the very atmosphere above you is being stripped away, atom by atom, like a cosmic sandblaster dissolving a sculpture that took millions of years to form. Imagine that this place is real. That astronomers have found it. That it exists right now, at this very moment, somewhere out there in the darkness between the stars, and that it is just one of hundreds of worlds so strange, so violent, so utterly alien to everything we know, that our language barely has the vocabulary to describe them. We think we understand planets. We grew up with them. 9 of them on the classroom poster, then 8 after the Great Pluto debate, each one a familiar face. The red one, the ringed one, the blue marble we call home. We built our entire intuition about what a planet is, what it looks like, what it does, from these 8 examples. And for most of human history, that was all we had. 8 data points. 8 variations on a theme. And we looked at those 8 worlds and we said, yes, this is what planets are like. Rocky or gassy, large or small, close to the sun or far away, but within a recognizable range of normal, within the neighborhood of comprehensible. Then we started looking at other stars. And everything we thought we knew shattered like glass in a 2,000 km/h wind. The story of exoplanet discovery is one of the most breathtaking chapters in the history of human knowledge. It is a story that begins with ancient philosophers staring at campfires and wondering whether those points of light in the sky might have worlds of their own. It runs through centuries of careful observation, through Galileo's telescope and Newton's mathematics, through the cold, long nights of patient astronomers cataloging stars one by one. And it reaches its modern crescendo in the late 20th century, when human ingenuity finally developed tools sensitive enough to detect planets around other stars, not by seeing them directly, which is almost impossibly difficult, but by reading the subtle signatures they leave on the light and motion of their host stars. The first confirmed detection of planets around another star came in 1992, when Alexander Woolston and Dale Frail announced the discovery of planets orbiting a pulsar, a dead star spinning hundreds of times per second, a zombie sun radiating deadly radiation in all directions. The very first exoplanets ever confirmed were already bizarre. And it only got stranger from there. Today, as we enter the 3rd decade of the 21st century, astronomers have confirmed the existence of more than 5,500 exoplanets, with thousands more candidates awaiting confirmation. These worlds have been discovered using a dazzling array of techniques: the radial velocity method, which detects the subtle wobble a planet imparts to its star; the transit method, which catches the dimming of starlight as a planet passes in front of its host; gravitational microlensing, which uses the bending of light around massive objects to reveal hidden worlds; direct imaging, which actually captures photons that have bounced off the surfaces or atmospheres of distant planets; and astrometry, which measures the precise positional wobble of stars across the sky. Each method has its own strengths, its own biases, its own blind spots. Together they paint a portrait of a galaxy teeming with worlds of every imaginable description, and many that we never imagined at all. And what a portrait it is! Stop for a moment and ask yourself this question. What does a planet have to be? What are the rules? Because when you look at what the universe has actually produced, you begin to suspect that there are no rules. Or rather, the rules are so much broader, so much more permissive, so much more creative than anything we came up with in our 8-planet classroom, that calling them rules feels almost like a joke. The universe is not constrained by our intuitions. It is not limited by our categories. It builds worlds the way a fever dream builds landscapes, with total disregard for what ought to be possible. There are planets made of diamond. There are planets so hot that their surfaces glow. There are planets with no star at all, wandering the darkness of interstellar space like cosmic orphans. There are planets where the year lasts less than a single Earth day. There are planets larger than Jupiter, itself so large that over 1,300 Earths could fit inside it, that orbit so close to their stars that their surfaces reach temperatures measured in thousands of degrees. There are planets that it rains iron. Planets that have two suns like something out of a science fiction movie. Planets that may be entirely covered in water hundreds of kilometers deep. Planets that orbit neutron stars, the crushed cores of dead suns so dense that a teaspoon of their material weighs as much as a mountain. Planets that seem to defy every model of planetary formation we have built. And each one of these worlds tells a story. Each one is a data point in the great project of understanding not just what other planets are like, but why the universe builds what it builds, and whether, somewhere in that vast and terrifying diversity, there might be a place that could support life. A place where, against all odds, something looks up at its own sky and wonders about us. That question, the question of life, of other minds, of whether we are alone, runs like a current beneath everything we are about to discuss. It is the reason exoplanet science is not just a technical curiosity but one of the most philosophically urgent endeavors in human history. Because every bizarre world we discover tells us something about the conditions under which planets form, evolve, and either nurture or destroy the possibility of life. Every hellish hot Jupiter, every diamond planet, every iron rain world narrows or expands the range of what we think is possible. Every discovery changes the calculation. So let us go on a journey. Let us leave the comfortable familiarity of our solar system and venture out into the strange, wild, magnificent diversity of worlds that fill this galaxy. Let us visit the most bizarre exoplanets ever discovered, not just as a list of exotic facts, but as a story about the universe's boundless creativity, about human ingenuity, about the nature of planets and the conditions for life. A story that, if you let it in, will permanently change the way you look at the night sky. Because those points of light are not just stars. They are suns. And around many of them, worlds are turning in the dark. Worlds stranger than anything we dreamed of. Let us begin with the one that rains glass. HD 189733b sits in the constellation Vulpecula, about 63 light-years from Earth. In cosmic terms, that is practically next door, a stone's throw in a galaxy that spans 100,000 light-years. It was discovered in 2005 using the radial velocity method, detected through the subtle gravitational tug it exerts on its host star. At first glance, it might seem like just another hot Jupiter, one of those massive gas giants that orbit absurdly close to their stars. But look closer, and HD 189733b reveals itself to be one of the most terrifying environments ever discovered by human science. The planet's deep blue color might make it look, from a distance, somewhat like Earth. Astronomers determined its color through a clever technique, observing how the reflected light from the planet changed as it moved behind its star and re-emerged. The result was startling. HD 189733b is a vivid, deep cobalt blue. For a moment, you might think, how beautiful, how reminiscent of our own blue marble. But the similarity ends there, brutally. That beautiful blue color does not come from liquid oceans or clear skies. It comes from silicate particles in the atmosphere. Glass. The atmosphere of HD 189733b is filled with tiny particles of silicate, essentially glass, suspended in clouds and driven by winds of up to 8,900 kilometers per hour. 8,900. That is roughly 7 times the speed of sound on Earth. The fastest wind ever recorded on Earth was about 400 kilometers per hour during a tropical cyclone. The winds on HD 189733b are more than 20 times faster. Now imagine what those winds do with the glass particles. They hurl them sideways across the planet in a continuous, planet-wide storm that never stops. There is no eye to this storm. There is no calm region, no safe side, no shelter. The entire planet is wrapped in a howling shroud of glass-laden wind, with temperatures on the day side reaching over 1,000 degrees Celsius. The planet is tidally locked to its star, meaning one face is always pointed toward the blinding heat of the sun while the other faces the cold of space. But the winds are so powerful that they distribute heat around the globe, keeping even the night side brutally hot. There is no dawn on HD 189733b, no dusk, no cycle of day and night as we know it. There is only the unending, howling, scouring violence of a world trapped in a perpetual nightmare of its own atmosphere. Ask yourself this: if you could stand on the surface of HD 189733b for even 1 second, what do you think you would experience? Of course, the answer is nothing, because you would be dead in a fraction of that second, vaporized by the heat and shredded by the glass-laden wind. But try to imagine that moment of perception, that first millisecond of impossible consciousness on that world. The blue-white glare of a star so close it fills a third of the sky. The roar of wind like nothing ever heard on Earth. The sensation of glass moving through the air at speeds beyond comprehension. And then, mercifully, nothing. HD 189733b is classified as a hot Jupiter, a category of planet that, when first discovered in the mid-1990s, completely upended our understanding of how planetary systems form. The first hot Jupiter ever discovered around a sun-like star was 51 Pegasi b, found in 1995 by Michel Mayor and Didier Queloz, who would later share the Nobel Prize in Physics for that discovery. 51 Pegasi b orbits its star at just 1/20th the distance between Mercury and our Sun, completing a full orbit in just over 4 days. It has roughly half the mass of Jupiter. Nothing in our solar system even remotely resembles it. And yet it exists. And once astronomers knew what to look for, they found hot Jupiters everywhere. But here's the thing about hot Jupiters that made planetary scientists lose sleep. They should not exist where they are found. Jupiter-sized planets require enormous amounts of material to form. They need to accumulate rock, ice, and gas in a process that takes millions of years and requires the planet to form far from its star, in the cold outer regions of the disk of material that surrounds young stars. That is where the ice line is, the boundary beyond which water and other volatile compounds freeze into solid ice, providing the building blocks for massive planet cores. Close to the star, everything is too hot for that process to work. So how did these giants end up so close? The answer, which took years of modeling and debate to work out, is that they did not form there. They formed far out, where they were supposed to, in the cold outer reaches of their planetary systems. And then they migrated. Interactions with a disk of gas and dust still surrounding their young stars can cause planets to spiral inward, losing angular momentum and drifting closer and closer to the heat. This process, called disk migration, can take a hot Jupiter from its distant formation site all the way into a tight orbit close to the star over timescales of millions of years. And as it migrates, it can wreak havoc on everything else in the system, flinging smaller planets into space or into their star, scrambling orbits, reshaping the entire planetary architecture. Hot Jupiters are, in a very real sense, agents of chaos. And HD 189733b is one of the most studied of them all, a window into one of the most common yet most alien types of planetary environments in the galaxy. But HD 189733b is not unique in its extremity. Not even close. Consider WASP 76b. This planet, orbiting a star in the constellation Pisces about 600 light-years from Earth, was the subject of a stunning announcement in 2020 that made headlines around the world. Astronomers using the espresso spectrograph on the Very Large Telescope in Chile had detected something extraordinary in the data. Iron. Not iron in the planet's core, or in its rocks, but iron vapor in its atmosphere. And not just anywhere in the atmosphere. Specifically on the day side, where temperatures reach over 2,400 degrees Celsius, easily hot enough to vaporize iron. On the night side, which is much cooler, the iron vapor condenses and falls as rain. Iron rain. Liquid iron droplets, falling through the atmosphere of an alien world. The implications of this discovery are staggering. Think about what iron is. One of the hardest, most durable materials we know, the stuff of engines and skyscrapers and swords. On WASP 76b, It evaporates from the rock and rises into the atmosphere on the day side, is carried around to the cooler night side by ferocious winds, and then condenses and falls as rain. The planet is tidally locked, like so many hot Jupiters, so this process is continuous and permanent. The day side is an iron evaporation machine. The night side is an iron rain collector. And the divide between the two is a raging Terminator line where the two environments crash into each other in a perpetual atmospheric storm. Researchers from the Universidad de Ginebra, led by David Ehrenreich, were the ones who announced this discovery, based on observations that looked at how the iron signature changed as different parts of the planet's atmosphere passed across the face of the star during transit. The signature was strong and blue-shifted on the evening side, meaning iron-rich air was being blown from day to night, and dramatically different on the morning side. The asymmetry was the telltale sign of iron condensing and raining out on the night side. Iron rain. Stop and let that sink in. Iron rain. On Earth, iron requires temperatures of over 1500 degrees Celsius to melt, and even higher to vaporize. The entire Industrial Revolution was built on humanity's ability to extract and work with iron, to heat it in furnaces with great effort and transform it into tools. On WASP 76b, the atmosphere does this automatically, continuously, on a planetary scale. The sky is literally made of metal vapor. The clouds are iron clouds. And when the weather turns, or rather, when the planet rotates so that a given parcel of atmosphere moves from the blazing day side to the cooler night, it rains metal. Not drops of water, drops of iron. You have to ask yourself, what kind of universe produces this? What set of physical laws, operating with perfect mathematical precision, leads to a world where it rains iron? And the unsettling answer is our universe. These laws, this physics. The same rules that make raindrops fall on your roof also make liquid iron fall through the skies of WASP 76b. The universe does not care about our sense of what is normal. Now, while we are on the subject of things falling from the sky that have no business doing so, let us talk about another category of utterly bewildering exoplanets: super-Earths and mini-Neptunes, and in particular, the water worlds. Among the thousands of exoplanets discovered by NASA's Kepler Space Telescope, launched in 2009 and operating until 2018, responsible for the discovery of the majority of confirmed exoplanets, a significant proportion fall into size categories that simply do not exist in our solar system. Our solar system has rocky planets up to Earth's size and then jumps all the way to Neptune, which is 4 times Earth's diameter. There is nothing in between. But in the broader galaxy, planets in that intermediate range, between 1 and 4 times Earth's radius, are actually among the most common types of planets known. Super-Earths and mini-Neptunes, they are called, and they represent a fascinating mystery. Are they giant rocky worlds with thin atmospheres like oversized Earths, or are they small gas worlds with thick volatile envelopes, or something else entirely? Something else entirely, it turns out, for some of them. Something else that involves water in quantities that beggar belief. GJ-1214b is a super-Earth orbiting a red dwarf star about 48 light-years away. It has a radius about 2.5 times Earth's and a mass about 6 times Earth's. These numbers alone put it in a category we have no solar system analog for. But what makes it truly strange is its composition. When astronomers modeled what could explain its size and mass, specifically its bulk density, which is lower than you would expect for a pure rock world, they found that it must contain a substantial fraction of water. Not just surface water, not just oceans. A deep, globe-spanning layer of water that extends from the surface downward for thousands of kilometers. Some models suggest that the interior of GJ-1214b is predominantly water, perhaps with exotic phases of ice that only exist under extreme pressure. Ice phases that do not exist anywhere on Earth. Ice that is actually denser than liquid water, formed when pressure squeezes water molecules into crystal structures unlike anything in our experience. And here is where it gets truly mind-bending. Imagine a planet covered entirely by ocean. No continents, no islands, no dry land anywhere. Just water, stretching from pole to pole, horizon to horizon, in every direction. The oceans of Earth are on average about 3.5 kilometers deep. The hypothetical water layer on GJ 1214b could be hundreds of kilometers deep. At the bottom of such an ocean, the pressure would be incomprehensible, thousands of times greater than anything in Earth's deepest trenches. And under that pressure, water behaves in ways that we are still working to understand. It might form exotic ices, Ice 7, Ice X, phases of solid water that exist under enormous pressure even at high temperatures. The bottom of the ocean on GJ 1214b might be a layer of exotic solid ice, squeezed by the weight of hundreds of kilometers of water above it, utterly unlike anything on Earth. Does this world have life? Could it? Ask yourself, what would life look like on a world with no land? No tidal pools, no shorelines, no geological cycling of minerals from rocks into oceans. Earth's geology plays a crucial role in the chemistry of life. Volcanoes releasing carbon dioxide, rocks weathering to release minerals, plate tectonics cycling material between the surface and interior. On a deep water world, the ocean floor might be ice, preventing direct contact between the water and rock below. The chemistry could be completely different. Life, if it exists there, would have to solve completely different chemical puzzles than life on Earth did. It might not even be recognizable to us as life, or it might not exist at all. And yet the universe is so creative, so endlessly inventive in its physical processes, that we cannot rule it out. Some scientists have speculated that the interface between the water layer and the exotic ice below might provide energy gradients, differences in temperature, pressure, and chemistry that could potentially drive biological processes. This is speculation, to be clear, pure theoretical possibility. But it is the kind of speculation that keeps astrobiologists up at night. GJ 1214b is not the only water world candidate. Kepler 62f, Kepler 62e, and several other planets in the habitable zones of their stars may also be water worlds. And researchers using data from NASA's TESS telescope, the Transiting Exoplanet Survey satellite, launched in 2018 as the successor to Kepler, have continued to find candidates. The universe, it seems, builds water worlds readily, perhaps more readily than it builds anything like Earth. And that raises profound questions about what kind of life is actually the norm in the universe, if life is the norm at all. But let us leave the water worlds for now and venture into something even more extreme, something that sounds so much like science fiction that when it was first proposed, many scientists greeted it with deep skepticism. Let us talk about diamond planets. The idea of a diamond planet began with a star called 55 Cancri. This star, located about 40 light-years from Earth in the constellation Cancer, is part of a binary system and is slightly smaller and cooler than our Sun. It hosts a remarkable planetary system. 5 confirmed planets, ranging from a hot super-Earth to a gas giant in a wide orbit. One of those planets, 55 Cancri e, quickly attracted enormous attention. It is a super-Earth with a mass about 8 times Earth's and a radius about twice Earth's. It orbits its star at a distance of only about 2.5 million kilometers, compared to 150 million kilometers for Earth's orbit, completing a full year in just 18 Earth hours. 18 hours. A year. 18 hours long. The surface temperature on the day side of 55 Cancri e was initially estimated to be around 2,000 degrees Celsius. Hot enough to melt most rocks, hot enough to create a lava ocean. NASA's Spitzer Space Telescope detected variations in brightness as the planet orbited its star, suggesting that heat was not evenly distributed, consistent with a tidally locked world where one side faces perpetual day and the other perpetual night, separated by extreme temperature gradients. But the truly extraordinary claim about 55 Cancri e came from its composition. Based on the star's chemical makeup, specifically, its unusually high carbon-to-oxygen ratio compared to our Sun. Some researchers propose that the planet itself might be carbon-rich. And what is carbon under extreme pressure and temperature? Diamond. Researchers including Niku Madhusudhan at Yale University published a paper in 2012 suggesting that 55 Cancri E could be a carbon planet, with a substantial portion of its interior composed of diamond, essentially a giant diamond, as large as twice the diameter of Earth, wrapped in a graphite shell and possibly with a silicate mantle above. The paper caused a sensation. A planet made of diamond. Headlines around the world ran with it. And while subsequent research has complicated the picture, later analyses of the star's composition suggested its carbon-to-oxygen ratio might not be as extreme as initially thought, making the diamond interior less certain. The possibility has never been entirely ruled out. And more importantly, the research opened a window into an entirely new category of planetary possibilities. Carbon-rich stars do exist, and around them, carbon-rich planets might form. And in carbon-rich planets, under the right pressures and temperatures, diamond might be not just a gemstone but a common rock. Think about what that means for the concept of value. Diamond is precious on Earth because it is rare. Because it takes enormous geological forces operating over billions of years to create even small amounts of it deep in Earth's mantle, and volcanic eruptions to bring those tiny quantities to the surface. Diamond engagement rings, diamond-tipped drill bits, diamond necklaces, all premised on scarcity, all premised on the extraordinary rarity of this material. And now we are discovering that in other parts of the galaxy, there may be entire planets made of the stuff. Not just a vein of diamond in a mine, not just a pipe of kimberlite, a whole planet, diamond all the way down, for thousands of kilometers. The universe does not care about our economic systems. And if 55 Cancri E is indeed largely made of diamond, and the debate continues among planetary scientists, then it would be the most valuable solid object ever discovered. In purely economic terms, absurdly so. One estimate, made tongue-in-cheek by astronomers shortly after the 2012 paper, suggested that the diamond in 55 Cancri E's interior would be worth more than the entire global economy, several times over, and then some. Of course, you could never mine it. Of course, the mere attempt to get there would be so far beyond current human capability that it is not even worth discussing as a practical matter. But the point stands, what we consider precious and rare on Earth may be, in the broader context of the galaxy, an ordinary rock on an ordinary planet orbiting an ordinary star. It is a perspective-shattering thought. Now let us shift from planets that might be made of treasure to planets that probably should not exist at all. Let us talk about pulsar planets. Remember the very first exoplanets ever confirmed? The ones discovered in 1992 by Woolson and Frail? They orbit a pulsar. And pulsars are among the most extreme environments in the known universe. A pulsar is the remnant of a massive star that has died in a supernova explosion. When a star with a mass between about 8 and 20 times our Sun's mass exhausts its nuclear fuel, it collapses in on itself in a catastrophic implosion that releases more energy in a fraction of a second than our Sun will radiate in its entire 10 billion year lifetime. The outer layers of the star are blasted off in the supernova, while the core collapses to form a neutron star, an object perhaps 20 kilometers across but containing more than the mass of our Sun. In that tiny volume, the density is so extreme that protons and electrons are squeezed together to form neutrons. A teaspoon of neutron star material would weigh approximately 10 million tons on Earth. 10 million tons. The entire population of Earth, all 8 billion of us, weighs less than 1 billion tons. A teaspoon of neutron star outweighs all of us combined by a factor of 10. Neutron stars often spin very rapidly, sometimes hundreds of times per second, because of the conservation of angular momentum as they collapse. These rapidly spinning neutron stars emit beams of electromagnetic radiation from their magnetic poles, and as they spin, those beams sweep across space like cosmic lighthouses. When Earth happens to be in the path of those beams, we detect regular pulses of radio waves, X-rays, or gamma rays, hence the name pulsar. Now, a massive star exploding in a supernova would seem like the worst possible event for any nearby planets. And indeed, any planets that existed around the original star before the supernova would be vaporized, scattered, or flung out of the system entirely. The system would be sterilized utterly. And yet, Woolsey and Frail found planets around a pulsar. So where did those planets come from? The answer is not entirely settled, but the leading theories involve either the survival of some planetary material through the supernova. Perhaps the planets formed from the outer layers of the companion star that was consumed before the explosion, or, more dramatically, the formation of new planets from the disk of material ejected in the supernova. This second possibility is particularly stunning. Planets that formed from the ashes of a stellar explosion. Worlds that coalesced from the debris of one of the most violent events in the universe. Born from catastrophe. The pulsar planets discovered by Woolsey and Frail orbit the pulsar PSR B1257+12. There are at least 3 of them, designated A, B, and C. Planet B is roughly 4 times Earth's mass, and Planet C is roughly 3.5 times Earth's mass. By the standards of pulsar planets, these are fairly Earth-like in terms of mass. But they orbit a neutron star that is bombarding them with intense beams of radiation, X-rays, gamma rays, high-energy particles, at levels that would make the surface of any such planet completely lethal to any life as we know it. The radiation flux from the pulsar would be so intense, so energetic, so completely penetrating, that no material we know of could shield any organism from it. These planets exist in a radiation bath that would shred DNA, destroy chemical bonds, tear apart any biological molecule, and yet they exist. Orbiting a dead star, surviving in a radiation environment that should, by all rights, make any concept of life laughable. They are among the most haunting objects in the known universe. Real places, real worlds, orbiting a cosmic lighthouse that sweeps its deadly beam across them again and again, every fraction of a second, in an eternal rhythm of radiation. Some astronomers have speculated, perhaps with more poetry than science, that if life somehow found a way to arise on such a world, using chemistry based on radiation resistance, perhaps, or living deep underground in some shielded pocket, it would experience a sky unlike anything we can imagine. The pulsar itself, seen from the surface, might appear as a flickering point of intense light, pulsating at a rate faster than the eye can follow. The radiation environment might cause the thin atmosphere, if one existed, to glow with aurora-like effects, sheets and curtains of light created by high-energy particles slamming into atmospheric molecules. It would be beautiful and lethal, simultaneously and without contradiction. But pulsar planets are not the only planets that inhabit extreme radiation environments. Let us talk about planets orbiting magnetars, which are essentially neutron stars with magnetic fields of almost incomprehensible strength, trillions of times more powerful than Earth's magnetic field. No confirmed magnetar planets have been discovered yet, but the theoretical possibility exists, and if such planets were found, they would be subject to magnetic field strength so powerful that they would distort the electron clouds around atoms, fundamentally changing the chemistry of any molecules that existed on or near the surface. Physics as we know it would operate, but in a mode so exotic that any chemistry, any geology, any possible biology would be completely alien to anything we understand. We are just getting warmed up, because now we need to talk about something that has been haunting astronomers since the very first exoplanets were discovered. The rogue planets, the wanderers, the worlds without suns. When we picture a planet, we picture it orbiting a star. We picture it in the warm, or at least predictable gravitational embrace of a parent sun, going around and around in its ordained path. This is so fundamental to our concept of what a planet is that it is almost definitional. A planet, by the definition adopted by the International Astronomical Union in 2006, orbits a star. But the universe, once again, did not get the memo. There are planets in the galaxy, perhaps hundreds of billions of them, based on some estimates, that orbit no star at all. They were flung out of their birth systems by gravitational interactions with other planets, or perhaps were even formed in isolation from clouds of gas and dust that were too small to ignite as stars. They wander through the interstellar darkness, alone, starless, lightless. No sun rises over their horizons. No photons from a nearby star warm their surfaces. They drift through the cold between the stars, each one a silent, frozen world, or perhaps not so frozen, depending on what lies beneath. These are called rogue planets, or free-floating planets, or orphan planets. And they are not a theoretical curiosity. They have been detected. In 2021, a team using data from the Kepler Space Telescope and ground-based observatories reported the detection of what might be the largest population of rogue planets ever identified. Dozens of free-floating planet-mass objects in a region of sky in the direction of the galactic center. Because rogue planets do not transit any star and do not cause any star to wobble, they are almost impossible to detect by conventional methods. The primary way to find them is through gravitational microlensing. When a rogue planet passes almost exactly between Earth and a distant background star, its gravity bends and momentarily brightens the light from that star in a characteristic way. The brightening is brief, unique, and tells astronomers about the mass of the intervening object. The results have been startling. The frequency of these microlensing events suggests that rogue planets may outnumber stars in the Milky Way. Some estimates place the number of free-floating planet-mass objects in our galaxy at 1 to 2 times the number of stars, meaning there might be as many as 400 billion rogue planets in the Milky Way alone. 400 billion worlds, wandering in the dark, each one unknown, unlit, unnamed. Are they habitable? Could any of them support life? Here is where the science gets genuinely fascinating and where the line between research and speculation begins to blur, and we should be clear about that blurring. Most rogue planets would indeed be frozen, their surfaces at temperatures of a few tens of degrees above absolute zero, locked in an eternal deep freeze with no energy source to drive chemistry or warm any potential ocean. But not necessarily all of them. Some rogue planets might retain enough internal heat from their formation and from radioactive decay in their interiors to maintain liquid water beneath a thick ice shell. Much like we believe Jupiter's moon Europa maintains a liquid ocean beneath its ice, not because of the sun but because of the tidal forces Jupiter exerts on it. A rogue planet cannot benefit from tidal heating from a parent star, but if it is large enough and geologically young enough, its own internal heat might do the job. A rocky planet with the right composition and the right radioactive element abundances might, in theory, maintain liquid water in a subsurface ocean for billions of years, even wandering in the interstellar dark. And if that ocean contained the right chemistry, and if life had arisen there, or had been delivered there by a meteor impact from a more hospitable world that the rogue planet once passed close to, it might persist, evolving slowly in the deep dark beneath kilometers of ice, completely isolated from the universe above. This is speculative. This is theoretical. We have no evidence of life on any rogue planet. We barely have evidence of the planets themselves beyond their gravitational signatures. But the possibility exists within the laws of physics and chemistry as we understand them. And given the sheer number of these worlds that may exist, even a tiny probability of habitability multiplied by hundreds of billions of planets produces a potentially significant number of inhabited worlds. Worlds where life has never seen starlight, where the concept of a star, of a sun, would be as alien to that life as the concept of a rogue planet is to us. The thought is almost unbearably strange and profound. Let us come back from the darkness of interstellar space and return to the worlds that do orbit stars, but orbit them in ways that are still deeply strange. Let us talk about circumbinary planets. Planets with 2 suns. When the movie Star Wars was released in 1977, the image of Luke Skywalker gazing out across the desert of Tatooine at a binary sunset, 2 suns setting on the horizon simultaneously, became one of the most iconic moments in science fiction. At the time, many viewers probably assumed this was pure fantasy, a detail added for visual effect and drama, with no grounding in reality. Real planets, the assumption went, orbited a single star. 2 suns would mean chaotic, unstable gravity that no planet could survive. The universe, of course, disagrees. In 2011, the Kepler Space Telescope discovered Kepler-16b, the first confirmed planet to orbit 2 stars simultaneously. Dubbed the real-life Tatooine by an enthusiastic scientific community and press corps, Kepler 16b orbits both stars in its binary system in a wide orbit that takes it around both of them in about 229 Earth days. The two stars, one roughly 2/3 the mass of our Sun and one roughly 1/5 the mass of our Sun, orbit each other in a tight dance, and Kepler 16b circles this dancing pair at a distance that puts it in the cold outer regions of the system. Its surface temperature is probably around -90 degrees Celsius. Brutally cold, uninhabitable by any standard we care about. But that is almost beside the point. The point is that it exists. That a planet can orbit two stars in a stable, nearly circular orbit, swinging around a gravitational center that is itself in constant motion. And that from its surface, if it has a surface in any meaningful sense, as it appears to be a gas giant, two suns would indeed rise and set. The experience would be completely alien. The suns would sometimes appear close together, sometimes on opposite sides of the sky, sometimes one just rising as the other sets. Shadows would fall in two directions simultaneously. The color and intensity of daylight would change as the relative positions of the two stars changed. It would be disorienting, dazzling, and utterly unlike anything on Earth. Since Kepler 16b, many more circumbinary planets have been confirmed. Kepler 34b, Kepler 35b, Kepler 38b, Kepler 47c, the list keeps growing. And some of these are much more interesting habitability-wise than cold Kepler 16b. Kepler 47 is a system with at least 3 planets, one of which, Kepler 47c, orbits within the habitable zone of its binary pair, the region where temperatures would allow liquid water on the surface if the planet had a suitable atmosphere. Kepler 47c appears to be a giant planet, probably not rocky, but the discovery was significant as proof that habitable zone planets can exist in binary systems. This matters enormously for our search for life. It has been estimated that roughly half of all stars in the Milky Way are in binary or multiple star systems. If only single star systems could host planets, that would cut in half the number of potential planetary systems. But if binary systems can host planets, and they clearly can, then the population of potentially inhabited worlds in the galaxy potentially doubles. Every confirmed circumbinary planet expands our sense of where life might be found. And then there are the truly weird geometries. Multiple star systems with 3 or more stellar components can produce planetary orbits of extraordinary complexity. The Alpha Centauri system, our nearest stellar neighbor, contains 3 stars, the binary pair of Alpha Centauri A and B, and the more distant red dwarf Proxima Centauri. We know that Proxima Centauri hosts at least 2 planets, including the famous Proxima Centauri b, which orbits in the star's habitable zone. But Proxima b's environment is anything but gentle. Proxima Centauri is a red dwarf prone to violent stellar flares, and any planet in its habitable zone must orbit very close to the star to receive enough warmth, making it vulnerable to those flares. Red dwarf planets deserve their own extended discussion, because they represent the most common type of planetary system in the galaxy and also some of the most challenging for life. Red dwarfs, also known as M-dwarfs, are stars significantly smaller and cooler than our Sun, with luminosities that can be as little as 1/10 of 1% of the Sun's. They burn so slowly and so frugally that they can live for tens to hundreds of billions of years, far longer than the current age of the universe. Our Sun will live for about 10 billion years total. Many red dwarfs will outlast the universe as we currently understand it. And because they are so common, making up roughly 73% of all stars in the Milky Way, the question of whether red dwarf planets can support life is arguably the most important question in astrobiology. The problem is multiple and serious. First, habitable zone red dwarf planets must orbit so close to their stars that they are almost certainly tidally locked. One face perpetually toward the star, one face perpetually away. This creates extreme temperature contrasts, a blazing day side that might be too hot and a frozen night side that is definitely too cold. Between the two, there might be a narrow band, the terminator, where temperatures are moderate. Could life exist in that narrow band? In principle, perhaps. Atmospheric circulation could redistribute heat, moderating the extremes. Some models suggest that a thick enough atmosphere with the right composition could keep the planet habitable across a wider area. But this is uncertain. Second, and perhaps more critically, red dwarfs are extremely active when they are young, and even in their middle age, they produce stellar flares far more powerful in proportion to their baseline luminosity than our Sun does. These flares emit enormous amounts of ultraviolet radiation and X-rays, which can strip the atmospheres of close orbiting planets over time and bombard their surfaces with radiation lethal to life. The same stellar activity that was potentially involved in sparking chemistry on early Earth, lightning, ultraviolet light, energetic particles, becomes an ongoing assault on any life that tries to gain a foothold around a red dwarf. And yet, life is stubborn, and there are red dwarf systems that seem to be relatively quiescent, where the stellar activity is lower, where atmospheric stripping might be slower. TRAPPIST-1 is perhaps the most famous and most studied of these. A tiny, cool red dwarf just about 40 light-years from Earth, it hosts 7 planets, 6 of them roughly Earth-sized, and 3 of them in the habitable zone, a record number of potentially habitable planets around any single star. The discovery of the TRAPPIST-1 system, announced in 2017, sent shockwaves through the scientific community and the wider public. 3 potentially habitable worlds around a single star, all within the size range of Earth, all possibly rocky, all in a system close enough to study with future telescopes in unprecedented detail. NASA's James Webb Space Telescope, launched in December 2021 and beginning science operations in 2022, has begun studying the atmospheres of the TRAPPIST-1 planets, and the results so far have been mixed. Early data on TRAPPIST-1b, the innermost planet, suggested it lacks a thick atmosphere, but the habitable zone planets remain uncharacterized and the search continues. TRAPPIST-1 is remarkable for another reason. Because all 7 planets orbit so close to their tiny star, their orbital periods are very short. The innermost planet, TRAPPIST-1b, completes an orbit in about 1.5 Earth days, and even the outermost confirmed planet, TRAPPIST-1h, takes only about 19 days. And yet these planets are also remarkably close to each other in space. Standing on any of the TRAPPIST-1 planets, the neighboring planets would appear as disks in the sky, visible with the naked eye as more than just points of light, but as actual circles. On TRAPPIST-1d, for example, the neighboring planet TRAPPIST-1e would appear roughly as large as our moon does from Earth, perhaps slightly larger. Imagine looking up and seeing another world with your naked eye, not as a bright star, but as a disk, a sphere, its features perhaps visible with a good telescope. Imagine watching weather systems roll across the face of that neighboring planet. Imagine the philosophical weight of that view. The resonance of those orbits, by the way, is something else remarkable about TRAPPIST-1. The planets orbit in what is called a resonant chain. Their orbital periods are related to each other by simple integer ratios. TRAPPIST-1b orbits 8 times for every 5 orbits of TRAPPIST-1c, and so on through the chain. This kind of orbital resonance is a sign of the system's stability and also of how it formed. Planets locking into these resonant relationships as they migrated inward through the disk of their forming system. The mathematics of it are beautiful, a cosmic music of orbital mechanics. The universe is not random in its arrangements. It finds harmonic solutions, resonant states, ordered patterns even in the wild diversity of its creations. Now let us turn to something that challenges our entire concept of what a planet can look like from the outside. We have talked about what is in these worlds, their compositions, their temperatures, their rain of iron or glass. But what about their orbits? What about the shapes of the paths they trace through space? Most planets in our solar system orbit the Sun in nearly circular paths. This circularity is a consequence of how planets form. In the disk of material around a young star, where gravitational interactions tend to smooth out orbits into neat, nearly circular rings. But in many exoplanet systems, orbits are far from circular. They are highly elliptical, stretched, elongated, eccentric. And an eccentric orbit creates a profoundly different climate experience than a circular one. Consider HD 80606b. This is a planet about 4 times the mass of Jupiter orbiting a star roughly 200 light-years away. And its orbit is extraordinary. HD 80606b follows an orbit so elliptical that at its farthest point from its star, it is more than 3 times the distance of Earth from our Sun, a relatively cool, distant location. But at its closest, it swoops in to just 1/30th of Earth's orbital distance. Astonishingly close, closer than Mercury gets to our Sun. The entire journey from farthest to closest takes about 111 Earth days. And in that swing from far to near, the planet experiences a change in stellar radiation so dramatic that its atmosphere heats up by hundreds of degrees Celsius in a matter of hours. Astronomers using the Spitzer Space Telescope actually observed this heating in real time. They watched the planet's thermal emission as it came screaming in from the far point of its orbit toward its star, and they saw the dayside temperature spike by about 700 degrees Celsius in just about 6 hours. 6 hours. In 6 hours, the temperature on this planet changed by 700 degrees. That is like heating your oven every few months from room temperature to a temperature hotter than the surface of many stars, and then letting it cool again over the course of a few months, and repeating this cycle forever. What would such a climate be like? The very concept of climate, which implies some kind of relatively stable average condition over time, barely applies. Instead, there would be periodic catastrophes. As the planet approaches closest approach, winds would roar around the globe as the heated dayside atmosphere expands and then rushes outward. Massive storm systems would form and dissipate on timescales of hours. Chemistry in the atmosphere would be driven by rapid heating cycles unlike anything in our solar system. And then, as the planet swings back out into the cold, the atmosphere would cool, perhaps allowing different chemical species to condense and fall as rain. Possibly a different kind of rain at each point in the orbit, as different compounds reach their condensation temperatures. HD 80606b is a natural laboratory for the most extreme atmospheric dynamics ever observed in a planetary system. And it is completely real. We must also talk about a class of planets that has prompted one of the most heated debates in planetary science. The superpuff planets. The cotton candy planets. The worlds with densities so low that they seem to violate everything we think we know about how planets are built. A planet's density is, in principle, straightforward to determine. You measure its size from transit observations, how much of the star's light it blocks, and its mass from radial velocity measurements, how much it makes the star wobble, and divide mass by volume. Simple. Except that when astronomers do this for some planets, the numbers come out absurd. Densities lower than styrofoam. Densities lower than balsa wood. Densities, in the most extreme cases, approaching that of aerogel, the famous silica foam so light it is almost transparent. Kepler 51b is one of the most notorious examples. It was discovered in 2012 orbiting a young star about 2,300 light-years away. Its radius is about 7 times Earth's, in the gas giant category, but its mass is only about 3 times Earth's mass. Wait, a planet 7 times Earth's radius in diameter but only 3 times Earth's mass? Run the numbers on that and you get a density of about 1/10 the density of water. 1/10. Water floats on most other liquids because it is denser than them. A substance with 1/10 water's density would be almost unimaginably fluffy. Kepler 51b is essentially a planet-sized ball of very light gas, with a density that has been compared to cotton candy. How can this be? The current best explanation involves these planets being young, geologically speaking, and having retained enormous, puffed-out gas envelopes that are slowly being eroded away by the radiation from their host stars. Photoevaporation, the same process that is slowly stripping the atmosphere from HD 1897333b, just much more dramatically, might be actively deflating these superpuff planets. What we see today may be a phase they are passing through. Give them 1 billion years, and they might shrink to something much denser and more normal-looking. Another leading explanation involves clouds of photochemical aerosols, haze particles formed by chemical reactions driven by starlight, high in the atmosphere, creating a planet that appears much larger in transit than its actual dense interior would suggest. Like seeing a planet wearing an enormous, puffy coat of haze. In 2022, observations with the James Webb Space Telescope of Kepler 51d, a sibling planet in the same system, provided tantalizing new information. The lack of certain spectral features suggested that clouds or hazes were indeed present, consistent with the photochemical haze theory. But the mystery is not fully solved. Superpuff planets remain some of the most puzzling objects in the exoplanet catalog. Ask yourself this: if you could visit a superpuff planet, if you could approach it in some hypothetical spacecraft, what would it look like from close range? Perhaps something like a giant cloud, a spherical nebula of haze and gas, with no clear surface, no boundary between atmosphere and space, just a gradual thickening of gas as you descended, the haze growing thicker and more opaque, the temperature rising, the pressure building, until eventually you reached a dense core hidden somewhere in the murk below. A core that might be solid, or liquid, or some exotic high-pressure phase of matter. You would never find a surface to land on. You would just sink. In some ways, that is true of all gas giants. Jupiter has no surface either. At some point, the gas just gets denser and denser until it becomes what scientists call a fluid, but not a liquid in any conventional sense. Hot Jupiter gas giant chemistry at high pressures involves phases of matter, metallic hydrogen, for instance, that do not exist under normal terrestrial conditions. We know this from our study of Jupiter itself. But the extreme versions of this phenomenon, as found in the most bizarre exoplanets, push these conditions to levels that are barely imaginable. Speaking of Jupiter, let us talk about a planet that makes Jupiter look modest. HAT P32b is a hot Jupiter with a radius about 2 times Jupiter's, meaning it is roughly twice the size of the largest planet in our solar system. That alone would make it remarkable. But what makes it deeply strange is what it is made of. Despite being so large, it has less mass than you would expect for a planet that size. Its density is very low. It is, in essence, a bloated, puffed-up gas giant, its atmosphere heated to high temperatures and expanded by the intense radiation of its nearby star. This process, the thermal inflation of gas giant atmospheres by stellar radiation, is called the inflation problem in hot Jupiter research, and it has not been fully solved. The radii of many hot Jupiters are larger than models of planetary structure predict they should be, even accounting for the stellar heating. Some additional mechanism, perhaps ohmic dissipation, where electrical currents induced by interactions between the magnetic field and the atmospheric winds generate heat in the interior, must be at work. The diversity of hot Jupiters is in itself a remarkable zoo. Some are dense and compact. Some are inflated. Some have winds strong enough to drive titanium oxide from the day side to the night side, where it condenses into clouds of exotic metal oxides. Some show evidence of atmospheres being actively stripped away into space, leaving a comet-like tail of gas. These are called evaporating planets, or in some cases, Chthonian planets, stripped giants from which so much atmosphere has been lost that all that remains is a bare, dense core, a rocky or metallic object with no gas envelope at all. The concept of a Chthonian planet is haunting. Imagine Jupiter over the course of billions of years, slowly losing its great atmosphere. The swirling bands, the great red spot, the complex chemistry of its clouds, all of it steadily ablated away by the radiation of an impossibly close star. The gas giant deflating slowly over geological timescales, shrinking from a giant to something modest, until eventually it is just a core, a hot, dense, naked rock, former king of a solar system, reduced to a bare remnant. Some researchers have proposed that some of the super-Earths and mini-Neptunes we observe around other stars might actually be such stripped former gas giants. They lost the game of planetary survival. They are what is left after the star wins. Now let us venture into the realm of the truly exotic. Planets around the strangest types of stars. We have talked about pulsars. Let us talk about white dwarfs. A white dwarf is what our Sun will become in about 5 billion years. When a star of low to intermediate mass, up to roughly 8 times the Sun's mass, runs out of nuclear fuel, it puffs up into a red giant, sheds its outer layers as a beautiful planetary nebula, and leaves behind its core a hot, dense, white dwarf. This object is roughly Earth-sized but contains roughly the Sun's mass, making it extraordinarily dense. 1 teaspoon of white dwarf material weighs about 15 tons. It glows from residual heat but has no nuclear reactions powering it. It simply cools over billions of years, eventually becoming a cold, dark black dwarf, though no black dwarfs yet exist in the universe, because the universe is not old enough for any white dwarf to have fully cooled. Can planets exist around white dwarfs? This is a question that was partly answered in 2020, in a discovery that sent ripples through the astronomical community. A team led by Andrew Vandenberg at MIT announced in Nature the discovery of what appeared to be an intact giant planet transiting a white dwarf, the first such planet ever found. The white dwarf, WD 1856 plus 534, is located about 80 light-years from Earth, and orbiting it every 1.5 days is a planet estimated to be at least several times Jupiter's mass. The fact that this planet still exists is remarkable. When its host star was a normal star like our Sun, the planet would have been much farther away, perhaps in the equivalent of our Jupiter's orbit. As the star evolved into a red giant, the planet should have been engulfed or at least severely disrupted. Instead, it survived, and at some point ended up in a very close orbit around the resulting white dwarf. The exact mechanism is unclear. It might have been driven inward by gravitational interactions with other planets in the system, or by some other dynamical process during the chaotic transformation of the star from red giant to white dwarf. But WD 1856b is not the most extreme example of white dwarf planetary weirdness. 4 years before this direct detection, astronomers had been observing a different and more indirect sign of planetary material around white dwarfs: pollution. The atmospheres of white dwarfs are extremely simple. Hydrogen and helium, the lightest elements, dominate because heavier elements quickly sink due to the intense surface gravity. Any heavier elements in the atmosphere would disappear from view within days to millions of years, depending on the type of white dwarf. Yet a significant fraction of white dwarfs, perhaps 25 to 50%, show heavy elements like calcium, iron, magnesium, and silicon in their spectra. These must have been deposited recently from some external source. The most likely source: rocky bodies, asteroids, comets, or planetary fragments, being disrupted and accreted onto the white dwarf. Some white dwarfs even show evidence of what appear to be rings of debris, disks of material surrounding the dead star, remnants of a destroyed planet, swirling in a permanent funeral procession around a stellar corpse. And in at least one remarkable case, astronomers have detected what appears to be a chunk of asteroid or small planet actively spiraling in toward the white dwarf, going to its doom. These observations give us a unique window into the composition of rocky planets and bodies around other stars. When a rocky body falls into a white dwarf and its elements pollute the atmosphere, astronomers can actually read off the chemical composition, the ratios of elements in the accreted material. And what they find is striking. The compositions are broadly similar to rocky bodies in our own solar system. The same basic chemistry, the same building blocks: oxygen, silicon, magnesium, iron, in roughly similar proportions. This suggests that the process of rocky planet formation is fairly universal, that the same elemental recipe is used across the galaxy to bake rocky worlds. The baking conditions vary, the exact recipe has variations, but the basic ingredients are the same. This universality of planetary composition is one of the most reassuring findings in all of exoplanet science. It suggests that rocky, Earth-like worlds are not unique to our solar system's peculiar history, but are a natural and common product of stellar evolution throughout the galaxy. But now let us consider something that throws this reassuring picture into chaos: the question of planetary system architecture. Because it turns out that not only are individual planets bizarre, but the arrangements of planets within their systems can be equally, if not more, mind-bending. Our solar system has a specific architecture: 4 rocky planets in the inner system, followed by an asteroid belt, followed by 4 giant planets in the outer system, with the whole thing lying in a remarkably flat plane and orbiting in the same direction. This seems orderly and logical. But look at other systems, and you see arrangements that make our solar system look like the exception rather than the rule. The Upsilon Andromedae system was one of the first multi-planet systems discovered around a main sequence star, announced in 1999. It contains at least 4 planets, with 3 of them being hot Jupiters. But one of the remarkable features of this system is that 2 of the giant planets orbit in a peculiar gravitational relationship to each other. Their orbital planes appear to be significantly inclined relative to each other, unlike anything in our solar system. Their orbits are tilted with respect to each other by a significant angle, suggesting a chaotic dynamical history, perhaps a past planetary scattering event where gravitational interactions between planets sent them careening into their current tilted paths. Planetary system architectures come in many forms that we had never imagined from our single data point of the solar system. Some systems have multiple super-Earths packed in tightly together in the inner system, with orbital periods of just days, all in nearly circular orbits locked in resonance chains. These systems, compact, tightly packed systems of inner planets, are among the most common types found by Kepler. Our solar system, with its empty inner zone above Earth-sized and its giant planets pushed far out, is actually unusual. Systems with hot super-Earths, not hot Jupiters, may be the most common type in the galaxy. This raises an uncomfortable question. Is our solar system normal? Are we the weird ones? The evidence increasingly suggests that we might be. Our lack of a super-Earth in the inner system, our enormous gaps between the small rocky planets and the giant planets, separated by an asteroid belt, our relatively circular and coplanar orbits, these might be the unusual features. Jupiter's presence as a guardian, using its gravity to deflect incoming comets and asteroids that might otherwise bombard Earth more frequently. This arrangement, which may have played a role in stabilizing Earth's environment enough for complex life to develop, might be rare. The rare Earth hypothesis, proposed by Peter Ward and Joe Kirschvink among others, argues that complex multicellular life requires a very specific set of planetary and galactic conditions, and that these conditions might be so rarely met that complex life is extremely uncommon in the universe. The bizarre diversity of exoplanet systems we have discovered can be read as supporting this view. Most planetary systems are architecturally so different from our own that replicating Earth's specific history of life seems improbable. And this is an equally valid interpretation, life is so adaptable, so capable of finding a way, that it might arise under conditions we cannot imagine, in planetary systems we would consider utterly hostile. The discovery of extremophiles on Earth, organisms that live in boiling hot springs, in acid, in the crushing depths of the ocean, in the hypersaline waters of salt lakes, in the radiation-drenched rock of nuclear reactor walls, has consistently expanded our sense of where life can go. Life on Earth has colonized every conceivable niche. Why should life elsewhere be constrained to niches we find comfortable? This tension, between the rare Earth view and the cosmic optimism view, runs through all of astrobiology and will not be resolved until we actually find life somewhere else. And exoplanet science is the best tool we have for narrowing down where to look. Let us talk about one more category of deeply strange worlds before we get to some of the most recently discovered and most startling exoplanets of all. Let us talk about lava worlds. Lava worlds are exactly what they sound like. Planets with surfaces partly or wholly covered in molten rock. They are rocky planets, but their surfaces are so hot, due to proximity to their stars and/or intense tidal heating, that rock exists as liquid. Magma oceans, not metaphorical but real, liquid rock stretching from horizon to horizon. And they are not hypothetical. They are the natural consequence of placing a rocky planet very close to a hot star. 55 Cancri E, which we discussed as a possible diamond planet, is also a candidate lava world. Given its surface temperatures of around 2000 degrees Celsius, much of the surface rock would likely be molten. Some researchers have suggested that it has a hemispherical lava ocean on its day side, a vast, quietly churning ocean of liquid rock on the sun-facing side, while the night side cools enough for the lava to solidify. In between, at the terminator, The transition from liquid rock to solid rock would be a coast of sorts, a shoreline made of magma, constantly changing as material flows and cools and is reheated. Kepler 10b is another candidate. It is a super-Earth orbiting very close to its star, with surface temperatures high enough to melt rock. Its density is consistent with a rocky composition, making it a prime candidate for a lava world. And if it is indeed a lava world, its surface geology would be completely alien to anything on Earth. No plate tectonics as we know it, because the surface is liquid. No volcanism in the traditional sense, because the entire surface is already volcanic in a way. Just a global ocean of silicate melt, slowly churning, evaporating rock vapor into its thin atmosphere, a world of fire and liquid stone. Corot 7b is another lava world candidate, notable for being one of the first super-Earths discovered with a well-determined density. Its surface conditions are so extreme that a team of researchers, Leger and collaborators, proposed in 2011 that it might experience rock rain. Not just iron rain as on WASP 76b, but rock rain. At the temperatures of its dayside, silicate rocks would vaporize, rise into the atmosphere, be carried to the cooler night side, and then condense as molten droplets of rock that would rain down. The geological cycle on such a planet is not a slow, billion-year process of uplift and erosion and plate tectonics. It is an atmospheric cycle, rock going through gas and liquid phases in the atmosphere on timescales of days. Rock rain. We are not in Kansas anymore. Now let us talk about some of the most recently discovered strange worlds, discovered with the James Webb Space Telescope and announced in just the past few years, because the pace of discovery in this field is breathtaking and the most exciting chapter may be the one we are living through right now. In 2023, observations by the James Webb Space Telescope of the rocky planet TRAPPIST-1c, the second planet in the TRAPPIST-1 system, and one of the candidates that had generated excitement as a potential habitable world, produced results that were deeply informative, if not what everyone hoped. TRAPPIST-1c receives about the same amount of radiation from its star as Venus does from our Sun. Researchers had hoped to detect signs of a substantial atmosphere, perhaps a thick carbon dioxide atmosphere like Venus, or something more exotic. What they found instead was a thermal emission consistent with a bare rock surface with little to no atmosphere, or at most a thin, tenuous atmospheric envelope. The dream of TRAPPIST-1c as a Venus twin, or something even more interesting, was deflated somewhat, though not definitively ruled out. More recently, in 2024, the James Webb Space Telescope made one of its most significant atmospheric detections yet: the identification of carbon dioxide and other molecular species in the atmosphere of a sub-Neptune planet called K2-18b. K2-18b is a planet with about 8.5 times Earth's mass and about 2.5 times Earth's radius, orbiting in the habitable zone of a red dwarf star about 120 light-years away. The detection of carbon dioxide was not the most dramatic part of the announcement. However, it was the potential detection of a molecule called dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by marine phytoplankton and other biological organisms. It is considered a potential biosignature, a chemical sign of life. The detection of a potential DMS signal in K2-18b's atmosphere was explosive news. But we must be very careful here. The DMS detection was tentative, at a low statistical significance, below the 5 sigma threshold that scientists typically require to consider a detection reliable. The researchers themselves were careful to say that the data was consistent with DMS but not conclusively confirmed. And there are possible non-biological explanations for the signal. Some abiotic chemical processes might also produce DMS, though no known abiotic process on Earth does so in significant quantities. The signal needs to be confirmed by future observations. Further James Webb observations of K2-18b were planned and are being analyzed. What is K2-18b? If it has the composition suggested by its size and mass, and the chemical detections made so far, it might be what some researchers call a Hycean world, a hydrogen-rich atmosphere world with a vast ocean of liquid water beneath it. The portmanteau combines hydrogen and ocean. If K2-18b is indeed a Hycean world, its liquid ocean would be covered by a thick hydrogen atmosphere that would create a kind of pressure cooker effect, keeping the ocean liquid even far from the star. And if its ocean is liquid, and if some biological-like process is producing DMS in that ocean, then the implications are almost too large to articulate. We would not be alone. But again, tentative, uncertain. The most important three words in responsible science. We do not know. Not yet. But the fact that we are having this conversation, the fact that we are seriously discussing whether a chemical signal from a planet 120 light-years away might be biological in origin, is itself astonishing. It is a measure of how far our technology has come, how sensitive our instruments have become, how close we might be to an answer to the oldest and most profound question humanity has ever asked. Are we alone in the universe? The answer might come from the atmosphere of K2-18b, or from the TRAPPIST-1 planets, or from some world we have not yet discovered, around some star we have not yet looked at closely enough. But it is coming. The machinery of discovery is in motion and it is accelerating. The James Webb Space Telescope is the most powerful observatory ever deployed for studying exoplanet atmospheres, and it is only a few years into its planned 10 to 20-year mission. Future telescopes, the European Extremely Large Telescope on the ground, the proposed Habitable Worlds Observatory in space, will be even more powerful. The pace of discovery is not slowing. It is accelerating. Let us take stock for a moment and ask ourselves a broader question. We have visited worlds where it rains glass, rains iron, rains rock. Worlds covered in diamond or lava. Worlds orbiting neutron stars and white dwarfs. Worlds with two suns and worlds with no sun at all. Worlds with densities lower than cotton candy and worlds made of iron vapor. What does all of this tell us? What is the universe trying to say with this incredible diversity? One thing it tells us is that the universe is an enormously more creative engineer than we are. Every type of planet we have described obeys the same laws of physics that govern Earth, but those laws, given different initial conditions, different amounts of different elements, different stellar environments, produce outcomes that our Earth-centric imagination never envisioned. We built models of planet formation based on what we saw in our own solar system, and then the universe showed us that our models captured only a small slice of the actual range. We revised our models, and the universe showed us something even more extreme. This has happened repeatedly in the short history of exoplanet science, and it will almost certainly happen again. This is how science works at its best. Not as a smooth accumulation of facts, but as a series of paradigm crashes, where the data from the real world demolishes our confident assumptions and forces us to rebuild our understanding from the ground up. The discovery of hot Jupiters in 1995 was one such crash. The discovery of the first pulsar planets in 1992 was another. The TRAPPIST-1 announcement in 2017 was another. Each one forced a revision of what we thought was possible, what we thought was common, what we thought planets were. And the revisions are not just about what types of planets exist. They are about the history of planetary systems, about the migrations and scatterings and gravitational dances that shape systems over billions of years. They are about the chemistry of atmospheres, about which molecules form under which conditions and what those molecules tell us about the story of a planet's evolution. They are about the question of life, about whether the conditions for biology are common or rare, whether life is a fluke or an inevitability, whether our biosphere is a precious, lonely miracle or one of trillions. Let us now go deeper into some specific worlds that have not yet gotten the attention they deserve. Worlds that are quietly sitting in the catalog of exoplanets and radiating strangeness. KELT-9b. If HD 1897333b is terrifying and WASP 76b is astonishing, KELT-9b is something else entirely. It is the hottest exoplanet ever discovered. It orbits a star that is itself extremely hot and luminous, a young, blue-white star called KELT-9, classified as an A-type star. KELT-9b completes its orbit in just 1.5 Earth days, at a distance so close that it is exposed to the most ferocious irradiation of any known planet. Its dayside temperature reaches about 4,300 degrees Celsius. 4,300 degrees. The surface of our Sun is about 5,500 degrees Celsius. KELT 9b, a planet, is nearly as hot as the surface of our star. It is hotter than most stars in the universe. Hotter than every red dwarf, every orange dwarf, most yellow dwarfs like our Sun. It is a planet that is nearly a star in terms of temperature. At these temperatures, not just iron vaporizes. Not just rock vaporizes. Molecules themselves cannot exist. The thermal energy is so intense that it breaks molecular bonds, water, carbon dioxide, methane, all the molecules we normally think of when we think of planetary atmospheres, simply cannot exist on the dayside of KELT 9b. Instead, the atmosphere consists of atomic species and ions, individual atoms of iron, titanium, sodium, and other elements, floating in a plasma-like superheated gas. Spectroscopic observations have confirmed the presence of many of these species. The dayside atmosphere of KELT 9b is a zoo of exotic atomic ions. And the star is not done yet. KELT 9 is a rapidly rotating star that emits enormous amounts of ultraviolet radiation, and this radiation is evaporating KELT 9b's atmosphere at a spectacular rate. Some estimates suggest that the planet is losing several hundred kilotons of mass per second. Hundreds of thousands of tons of atmosphere bleeding off into space every single second. The planet has a comet-like tail of escaping gas, trailing behind it in its orbit. Over the lifetime of the star, which, being massive and hot, will live only a few 100 million years before exhausting its fuel, KELT 9b may lose a significant fraction of its atmospheric mass. KELT 9b is, in a very real sense, a dying world. It formed, migrated close to its star, and is now being slowly eaten alive by the stellar radiation. In cosmological terms, it is a brief phenomenon, perhaps only 10 to 100 million years of existence in its current state before either the star evolves and destroys it more violently, or the atmosphere is stripped to a bare core, or some other catastrophe ends its existence. It is a planet in the process of being erased. A temporary visitor to extreme conditions, writing its brief biography in escaping streams of metal vapor. Now let us talk about a world that is strange in a completely different way. Let us talk about Kepler 7b, and the discovery that some planets have their own distinct atmospheric color palette, essentially visible cloud features that can be mapped. Kepler 7b is a hot Jupiter about 1,400 light-years away. It was discovered early in the Kepler mission and is notable for being one of the lowest density hot Jupiters known at the time of its discovery. Another superpuff, roughly 1.5 Jupiter radii, but with significantly less than Jupiter's mass. But the truly remarkable discovery about Kepler 7b came in 2013, when NASA announced that Spitzer Space Telescope observations had been used to map the planet's thermal emission, to create a crude temperature map of different longitudes around the planet. The result was startling. The hottest region was not directly under the star, as you might naively expect for a tidally locked world, but was significantly offset to the west. This is consistent with powerful eastward jet stream winds, atmospheric dynamics that carry heat from the day side and deposit it on the night side at a specific longitude, offset from the direct substellar point. More dramatic was the announcement that the Kepler spacecraft itself, using optical light, had detected something at the western hemisphere of the planet that appeared brighter, a region that reflected more starlight. When combined with the Spitzer data showing that the same region was cooler, the conclusion was inescapable. Kepler 7b has clouds. Reflective clouds, probably made of silicate condensates, concentrated at specific longitudes, not uniform around the planet. The western hemisphere of Kepler 7b is persistently cloudier than the eastern hemisphere because of the complex interplay between dynamics, temperature, and condensation. This was the first exoplanet weather map, the first glimpse of the cloud patterns on another world. It was only crude, a broad, longitude-averaged picture, not the detailed swirling patterns we know from Jupiter or Earth. But it was a beginning. It was the first step on the road toward actually seeing weather on other worlds, toward watching storms on alien planets. And today, with the James Webb Space Telescope, we are beginning to do this with unprecedented sensitivity, detecting molecular species, inferring cloud properties, building atmospheric profiles for planets around other stars. The future of this field includes the possibility of something almost miraculous: detecting spectral features in the atmospheres of Earth-sized planets in the habitable zones of Sun-like stars. Detecting oxygen, detecting water vapor, detecting ozone, detecting methane, detecting combinations of molecules that, in the absence of life, would rapidly react and destroy each other. Disequilibrium chemistry, the kind that on Earth is maintained only because life is continuously producing oxygen and methane and other reactive species. If we ever detect such a disequilibrium chemistry on an Earth-sized planet in a habitable zone, we will have a very strong, though not conclusive, case for life. We are not there yet, but we are on the road. Let us now discuss a category of discovery that has remained controversial and fascinating in recent years: exomoons. The moons of exoplanets. We have more than 200 moons in our solar system, and they range from planetary-sized objects like Titan and Ganymede to tiny, irregular rocks just a few kilometers across. Moons can significantly affect the habitability of planets. Earth's moon stabilizes our axial tilt, which has played a role in maintaining relatively stable climates over geological time. And some moons, Europa and Enceladus, are among the best candidates for life in our solar system, not because they are in the habitable zone of the Sun, but because they have liquid water maintained by tidal heating. Finding exomoons is extraordinarily difficult. Even the largest moons in our solar system would be nearly impossible to detect with current methods around stars many light-years away. But astronomers have not given up. Two researchers in particular, David Kipping of Columbia University and his team, have been searching Kepler data systematically for exomoon signals, using a technique that looks for the subtle additional dimming and timing variations that a moon would cause around a transiting exoplanet. In 2018, Kipping and Alex Tichy announced what they described as the first candidate exomoon detection: a possible moon around Kepler 1625b, a large exoplanet in an orbit roughly similar to our Jupiter's distance from its star. The candidate moon, if real, would be roughly the size of Neptune, enormous by solar system standards, but perhaps not unprecedented in a galaxy where massive planets exist in all sorts of configurations. The detection was based on subtle anomalies in the transit light curve, tiny deviations from what you would expect from a pure planet transit. Subsequent observations with the Hubble Space Telescope produced additional suggestive evidence, but the detection remains contested. Other researchers analyzing the same data have reached different conclusions, arguing that the signal could be explained by stellar variability or other instrumental effects. The community remains divided. The exomoon has not been confirmed, but it has not been ruled out. Kipping's team has continued the search, and in 2022 announced another candidate, around Kepler 1708b, again suggestive but not conclusive. The hunt for exomoons continues, and the prize is enormous. If we can confirm exomoons, we can begin to characterize them, and the possibility of habitable exomoons, ocean-bearing moons in the habitable zone of their host systems, opens up an entirely new category of potentially life-bearing worlds. Consider, Ganymede, Jupiter's largest moon, is larger than Mercury. Titan, Saturn's largest moon, has a thick nitrogen atmosphere with complex organic chemistry on its surface. If such bodies existed around exoplanets, they would be a form of world distinct from anything in our standard categories. They would be worlds that orbit worlds. And they might be habitable in ways that are completely different from a planet in the habitable zone. If the exoplanet they orbit is a warm gas giant, perhaps the tidal heating from that giant keeps the moon's ocean liquid. Perhaps the planet provides a radiation shield. Perhaps the constant gravitational interaction provides geological energy that drives chemistry in the moon's interior. Life on an exomoon would experience a sky dominated by its planet. If the moon orbited a gas giant like Jupiter, the gas giant would fill a large fraction of the sky, its banded clouds visible in detail, its moons, siblings of the habitable moon, visible as bright objects at certain orbital positions. The complexity and beauty of such a sky is almost beyond imagining. The effects on tides, on climate, on the orbital dynamics of the system would all be unique to this kind of nested gravitational architecture. It is a real possibility, and we might confirm the existence of such a place within the next decade or two. Let us step back even further and consider what the collective pattern of all these bizarre exoplanets tells us about the Milky Way galaxy as a whole. Estimates based on the statistics of Kepler planet discoveries, extrapolated across the entire Milky Way, suggest that there are on average more than one planet per star in our galaxy. The Milky Way has roughly 300 billion stars. That means there are at least 300 billion planets. And based on the frequencies of various planet types found by Kepler, roughly 20 to 30% of Sun-like stars have an Earth-sized planet in the habitable zone. If this fraction applies across the galaxy, there could be tens of billions of potentially habitable Earth-like planets in the Milky Way alone. Tens of billions. And yet, we are here, apparently alone, as far as we can tell. We have not received a confirmed alien radio signal. We have not been visited, as far as we know from reliable evidence. We have not detected any sign of industrial civilization elsewhere in the galaxy. No Dyson spheres, no anomalous energy signatures, nothing that screams intelligent life. This is the Fermi paradox, named after the physicist Enrico Fermi, who allegedly asked at a lunch conversation in 1950 something like, "If the universe is so large and old and planets so common, where are all the aliens?" The silence of the universe, in the face of so many potentially habitable worlds, is one of the deepest mysteries in all of science. Every bizarre exoplanet we discover adds a piece to this puzzle. Hot Jupiters that migrated and destroyed inner rocky planets. There goes a planetary system's habitability. Pulsar planets in lethal radiation environments. There goes another. Rogue planets wandering in the dark. Potential habitats but severely limited. Water worlds with no land and perhaps no geochemical cycling. Maybe life, maybe not, but maybe not intelligent life. Superpuff planets too diffuse to have solid surfaces. Lava worlds too hot to sustain any chemistry we know. Diamond planets with exotic chemistry we cannot predict. And yet, even with all of this weirdness, the numbers are so large. Tens of billions of potentially habitable worlds, just in the Milky Way. Even if only 1 in 1,000 of them actually develops life, that is tens of millions of life-bearing worlds. Even if only 1 in a million of those develops intelligence, that is tens of thousands of intelligent civilizations. In a galaxy so large that the nearest one might still be thousands of light years away. Close enough to exist, far enough to remain silent to our primitive instruments. Or perhaps intelligence is even rarer than that. Perhaps Earth is the only intelligent civilization alive in the galaxy right now. Perhaps the rare Earth hypothesis is correct and all of those other worlds, no matter how numerous, failed to climb the particular ladder of biological and geological coincidences that led to us. Both possibilities are terrifying in their own ways. If we are alone, the responsibility of being the only minds in the galaxy is a weight almost too heavy to contemplate. If we are not alone, the silence is its own kind of mystery, demanding explanation. The discovery of just one other instance of life, even microbial life, even dead fossil life on Mars, even a biosignature in the atmosphere of K2-18b or a TRAPPIST-1 planet, would resolve one part of this dilemma. It would tell us that life arises readily given the right conditions, that the universe is biologically productive, that we are not alone. And then the question becomes, why haven't we heard from anyone yet? That answer might be disturbing. Perhaps intelligence routinely destroys itself. Perhaps interstellar communication is fundamentally harder than we think. Perhaps the universe has already been visited, and the visitors have chosen not to contact us for reasons of their own. These are the questions that the study of exoplanets feeds into. It is not just about cataloging interesting rocks around distant suns. It is about understanding our place in the universe, about whether meaning and consciousness and complexity are the universe's great experiment, running in isolation on this one blue marble, or whether they are a recurring phenomenon, arising again and again wherever the conditions permit, filling the galaxy with minds that gaze up at their own alien skies and wonder the same things we wonder. Let us now consider a few more worlds that have not yet gotten their moment in the spotlight, but absolutely deserve one. GJ 3470b. This is a warm Neptune orbiting a red dwarf about 96 light-years from Earth. It was discovered in 2012 and classified as a hot Neptune, not as extreme as the hottest Jupiters, but extremely close to its star by solar system standards. What makes GJ 3470b remarkable is the rate at which it is losing its atmosphere. Observations with the Hubble Space Telescope detected an enormous hydrogen cloud surrounding the planet, evidence of atmospheric escape on a massive scale. The planet is losing mass at a rate that is extraordinary even among evaporating planets, leading researchers to estimate that it has already lost a significant fraction of its original mass and may eventually be stripped down to a dense, bare core. This process, photoevaporation, is one of the key shapers of planetary diversity in the galaxy. It is thought to be responsible for the so-called radius gap, or Fulton gap, a feature noted in the Kepler planet statistics. When you plot exoplanet radii, you see a distinct gap in the distribution between about 1.5 and 2 Earth radii. Very few planets have sizes in this range, even though smaller and larger planets are common. The explanation is photoevaporation. Planets in this size range exist in an intermediate zone where they are just barely able to hold on to or just barely losing their atmospheres. The ones that successfully retain their atmospheres grow to be mini Neptunes. The ones that lose their atmospheres shrink to bare rocky cores, super-Earths. And the in-between state is unstable and short-lived, leading to few planets in the gap. It is evolution. Not biological evolution, but atmospheric evolution, the survival of the atmospherically fit. The Fulton Gap is one of the most elegant observational discoveries in exoplanet science. It is a fingerprint of physical processes that operated on every close-orbiting planet in the galaxy billions of years ago, when they were young and their stars were active. It is a story written in the statistics of thousands of planets, telling us about a universal process that shaped the entire population of small planets in the Milky Way. GJ 436b. This planet is a warm Neptune orbiting a red dwarf about 33 light-years away. It was discovered in 2004 and is one of the closest known exoplanets. What makes GJ 436b fascinating is its internal composition. Based on its size and mass, its interior must contain a large amount of water, but not liquid water as we know it. At the pressures and temperatures inside GJ 436b, water would exist in a high-pressure solid phase. Specifically, a phase called Ice-X, an exotic crystalline form of water that exists only at extreme pressures and temperatures simultaneously. The planet might have an interior made of hot ice, water that is solid not because it is cold, but because the pressure is so extreme that it cannot flow even at temperatures above 1,000 degrees. This is sometimes called hot ice or superionic ice, and it is a genuinely exotic state of matter that was first predicted theoretically and has since been confirmed in laboratory experiments using extremely powerful lasers and shock waves to recreate the conditions. Hot ice. The universe's sense of humor is impeccable. Let us take a moment and think about what it means that we have learned all of this in just a few decades. In 1990, the catalog of confirmed exoplanets was empty. 0. The Hubble Space Telescope was launched in 1990. The same year its primary mirror was found to be flawed. The internet was just beginning to emerge from the academic world. Cell phones were brick-sized novelties. The human genome had not been sequenced, and astronomers knew of exactly 0 planets beyond our solar system. Today, we know of more than 5,500. We know their sizes, their masses, their orbital periods, their atmospheric compositions in some cases. We know they rain iron and glass. We know some of them are made of diamond. We know some of them orbit dead stars and some of them orbit 2 stars simultaneously and some of them orbit no stars at all. We know their atmospheres contain water vapor, carbon dioxide, methane, sodium, potassium, and possibly the biosignature of living organisms. In 35 years, humanity went from knowing 8 planets to knowing more than 5,500. And the rate of discovery is accelerating. The James Webb Space Telescope is finding things every week. TESS is continuously scanning the sky for new transiting planets. Ground-based spectrographs are detecting wobbles in star positions with ever-increasing precision. New missions are planned. Plato from ESA, planned for launch in the late 2020s, will survey tens of thousands of stars for Earth-like planets around Sun-like stars with unprecedented precision, targeting planets in the habitable zone with orbital periods similar to Earth's. The Ariel mission, also from ESA, will conduct the first systematic survey of exoplanet atmospheres, characterizing hundreds of them in a coordinated campaign. The Roman Space Telescope, formerly known as WFIRST, will use microlensing to find thousands of free-floating rogue planets, and will conduct a statistical census of planetary systems across a wide range of galactic environments. The next generation of ground-based telescopes, the 30-meter telescope and the Giant Magellan Telescope, both currently under construction, will collect enough light to directly image the reflected light from rocky exoplanets in the habitable zones of nearby stars, and to take spectra of those atmospheres. To look directly at the light coming from the surface and atmosphere of another Earth-like world, separated from the overwhelming glare of its host star, and read off what that light can tell us about what is happening there. We are approaching the moment when this becomes possible. And when we take that first spectrum of an Earth-sized planet in a habitable zone, when we see the molecular fingerprints in that light, we will know something about that world that no previous generation of humans could have imagined knowing. We will have crossed a threshold that separates the age when we could only wonder about other worlds from the age when we can actually study them. This is not science fiction. This is the roadmap of real institutions, real missions, real budgets being allocated by real governments and real space agencies. We are building the instruments. We are training the scientists. We are developing the techniques. The answer to the question of whether Earth is alone is within the reach of science in this century, perhaps in this generation. Now let us consider some of the most mind-bending speculative territory in exoplanet science. Not wild fiction, but serious theoretical work being done by serious scientists. What is the most extreme type of planet that physics permits? Is there a planet made entirely of iron? Is there a planet covered in a global superconducting ocean? Is there a world where the geochemistry runs on sulfur instead of oxygen, producing completely alien mineral assemblages? Could there be a world where life, if it exists, breathes something other than oxygen? Perhaps fluorine, the most reactive element, which can serve as an electron acceptor for metabolic processes. These are not crazy questions. They are asked by astrobiologists and planetary scientists who are trying to understand the full range of what physics and chemistry allow. Carbon-silicon hybrid planets, worlds with both carbon-rich and silicate-rich regions, producing exotic mineralogy at the boundary, have been theorized. Planets with sulfide oceans instead of water oceans. Planets with liquid nitrogen lakes at the surface, as Pluto was confirmed to have in 2015 when the New Horizons spacecraft flew past it and revealed a frozen nitrogen plain called Tombaugh Regio. Planets with liquid methane oceans, as Saturn's moon Titan has hydrocarbon lakes of liquid methane, with weather cycles based on methane evaporation, condensation, and rain, like a cold, chemically alien version of Earth's water cycle. It has been seriously proposed that Titan might harbor life based on a completely different biochemistry. Not water-based, not DNA-based, but using liquid methane as a solvent and some different set of organic molecules as the basis for heredity and metabolism. This is highly speculative, but it is grounded in real chemistry and has been the subject of real scientific papers. Around other stars, worlds like Titan, methane ocean worlds in the cold outer reaches of their systems, may be enormously common. Red dwarfs have habitable zones so close to the star that their outer systems, farther out, might host many Titan-like worlds in permanent cold, with methane chemistry cycling through their equivalent of seasons. Life based on methane chemistry, if it existed, would look completely different from anything on Earth. It might not even use carbon chain molecules as we know them. It might be silicon-based, or use some exotic solvent we have not thought of. The universe might have solved the problem of self-replicating chemistry in ways we cannot predict from Earth's single example. This is the frontier. This is the edge of what we know and what we dare to imagine. And every discovery, every new bizarre world, every new atmospheric signature, every new orbital architecture discovered around another star adds another piece to the puzzle. Consider what the discovery of truly alien life would mean, not just scientifically, but philosophically, culturally, religiously. Every major human religion has a conception of our place in the universe, and most of those conceptions were formulated when we thought we were alone, when the night sky was a backdrop of points of light rather than a forest of inhabited worlds. The discovery of even microbial life on another planet would trigger a re-evaluation of those conceptions at a depth that would make the Copernican revolution. The shift from an Earth-centered to a Sun-centered solar system in the 16th century looked modest by comparison. Copernicus moved us from the center of the solar system. The discovery of alien life would move us from the center of biology itself. And if intelligent life were discovered, if we received a confirmed, unambiguous signal from another civilization, the effect on human culture, philosophy, religion, politics, and psychology would be unlike anything in our recorded history. There is no comparison. It would be the single most significant event in the history of our species. Everything we thought we knew about our uniqueness, our significance, our destiny, would need to be reconsidered. This is not a reason to panic. It is a reason to prepare, to cultivate the intellectual and emotional tools to handle the discovery when it comes, if it comes. To broaden our minds to the possibility that the universe is full of life and consciousness and complexity, none of which we can predict from our single example. To approach the diversity of exoplanets not as a catalog of curiosities, but as evidence of a cosmos that is endlessly creative, that produces complexity everywhere it can, that writes its story in the chemical signatures and gravitational whispers of worlds we are only just beginning to read. Let us visit a few more worlds before we bring this journey to a close. Worlds that deserve to be known by name. Kepler 442b. This is a planet roughly 1 1/3 Earth size orbiting in the habitable zone of an orange K-type star about 1,200 light-years from Earth. It received the highest habitability rating of any known exoplanet on the Earth Similarity Index at the time of its characterization. A rating of about 0.84 on a scale from 0 to 1, where Earth itself is 1. This is based on its size, its estimated surface temperature, which suggests liquid water could exist, its stellar type, and other factors. Kepler 442b is, in the eyes of many planetary scientists, one of the best candidates for a world that might be genuinely Earth-like. Not just in size, but in the range of possible conditions it might experience. The answer so far has always been more than you thought, stranger than you imagined, more wonderful than you dared to hope. And the story is not over. It has barely begun. We are living in the age of exoplanet discovery, and every single day, new data flows in from telescopes in orbit and on mountaintops and in Antarctic observatories. New planets are confirmed. New atmospheric detections are made. New architectures of planetary systems are mapped. The catalog grows. The picture becomes richer, stranger, more complex. And somewhere in that complexity, the answer to the oldest question humanity has ever asked is hidden, waiting to be found. The next time you step outside on a clear night and look up at the stars, try to see them differently. Not as points of light, not as distant fires too far away to matter, but as suns, each one potentially circled by worlds, some rocky and warm and watery like Earth, some blazing infernos where iron rains from the sky, some frozen worlds of exotic ice, some cotton candy planets drifting through habitable zones, some rogue worlds wandering in the dark between them. Some of those stars have worlds orbiting them right now that we have not yet discovered. Some of those worlds might be nothing like anything we have described in this journey, They might be genuinely unprecedented, genuinely new categories of world that will require new words and new concepts to describe when we finally find them. The universe has surprised us repeatedly in the short history of exoplanet science, and there is no reason to think the surprises have ended. We are at the beginning. We are the first generation of humans who can point to specific stars and say, there is a planet there. We are the first who can say, that planet has water vapor in its atmosphere. That one has iron clouds. That one might possibly have life. We are the pivot point in history between the age when other worlds were dreams and the age when they become known facts. And if, in your lifetime, the James Webb Space Telescope or some future observatory reports the detection of a molecule in the atmosphere of a habitable zone planet that can only be produced by life, if that announcement comes in the next decade or the next generation, you will remember this moment. You will remember when you first understood that those points of light are suns, and around those suns are worlds, and on those worlds, impossibly, against all odds, or perhaps with perfect inevitability, something might be alive. That possibility alone makes every equation solved, every observation made, every cold night spent in a mountain observatory, every line of code written to analyze transit data, every photon collected by a mirror in space worth it. Worth everything. Because if we find it, when we find it, it will be the greatest discovery in the history of our species. And it begins with looking up and wondering. Now ask yourself one final question, the one that sits beneath all the others, the one that every bizarre, alien, extraordinary world in this catalog is ultimately pointing toward. If the universe can produce all of this, all of these impossible, magnificent, terrifying worlds, what else might it have produced that we have not yet imagined? What categories of existence are out there beyond the edge of our current knowledge, waiting to be found by future instruments, future minds, future curiosity that we are today only beginning to cultivate? The darkness between the stars is full of worlds, full of stories, full of possibilities we have not yet conceived. Go look up. The universe is waiting.